Hello world, it's Siraj, and our task today is to build a recurrent network, a type of recurrent network called an LSTM, or long short-term memory network, to generate M lyrics. That's our task. And we're going to build this without using any libraries, just numpy, which is for matrix math, because we want to learn about the math behind LSTM networks. We've talked about recurrent networks earlier on in the series, and LSTMs are the next logical step in that progression of neural network learnings. So that's what we're going to do today, and we're going to first talk about recurrent networks. We're going to do a little refresher on what recurrent networks are, how we can improve them, and then we'll talk about LSTM networks and how they are improvements and the mathematics behind them. Then we'll build all of this. Build as in I'm going to explain the code because there's quite a lot of code to go over here. There's a lot of code. But we're going to look at all the code, and then I'm going to code out manually the forward propagation parts for both the greater recurrent network and then the LSTM cell itself. So strap on with every math hat you have, because this is going to be so hard. We might as well just give up. Let's just forget this. No, I'm just kidding. No, this is actually going to be pretty easy. This is going to be pretty easy. If you got the recurrent net video, this is going to be pretty easy stuff. Although it's a little more complicated. But you will get this, okay? Get ready for this. I'm going to make sure you get this. Okay, so here we go. What is a recurrent network? Can you tell me what a recurrent network is in one sentence? I'll give you 10 seconds. Go. Okay, that's all the time you get. I'm not going to wait a full 10 seconds. Recurrent networks are cool. They're useful for learning sequential data. We know this. We know this. They're useful for learning sequential data. A series of video frames, text, music, anything that is a sequence of data, that's where recurrent networks do really well. That's what they're made for. They're very simple. You have your input data, and then you have your hidden state, and then you have an output. And so the difference between recurrent nets and feed-forward nets are that recurrent nets have something different here. So in a normal feed-forward net, we would have our input, our hidden layer, and then our output layer. And that's it. And then we would have two weight matrices between each of these layers that are those are matrices, right, that we multiply, right? Input times weight, add a bias, activate. Hopefully you said activate, because that is the wrap, slash mnemonic device. But input times weight, add a bias, activate, repeat over and over for feed-forward networks. The difference, though, for recurrent networks is that we add another weight matrix. And this other weight matrix, called synapse H in this diagram, connects the hidden state back to itself. So it's just a third weight matrix. And the reason we add that is so whenever we are training our network, we're not just feeding in new data points. So if we're trying to train a recurrent net to remember the next, to predict the next number in a series, and the series is 1 through 10, right? We want to predict the 10. We would say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We wouldn't just give it the numbers, we would also feed in the hidden state, right? So we would say, okay, so given a 1, predict the 2. Okay, now given the 1 and 2, predict the 3. Okay, given the 1, 2, and 3, predict the 4. And that's how we would train every iteration. But that's not all we would give it. We wouldn't just give it the input data, we would also give it the hidden state. We would give it both. And so that's why we have a recurrent matrix that's connecting the hidden state to itself, because we are not just giving it every new data point, the 1s and the 2s and the 3s, we're also giving it the hidden state, which is basically a matrix, and we're multiplying it by the hidden state and the new input data. We are feeding in the hidden state and the input data at every time step. And so that's why we have a hidden matrix. And so you could think of this as unrolled as just a series of feed-forward networks, right? Where we give it an input data point, and then we get a hidden state, and then in the next time step, we don't just give it this new data point x1, but we also give it the hidden state from the previous time step. So we just continue to do that. So that's one way of looking at a recurrent network, as just a big chain of feed-forward networks, a chain, right? A blockchain. No, not blockchain. Although I do want to talk about blockchain. It's coming, don't worry. I'm coming for you, blockchain, but not yet. We're still talking about recurrent networks. Amazing stuff, amazing stuff. Blockchain's coming though. Oh, I don't want to give away too much. I just did. Anyway. Okay. You guys can tell I'm very excited about blockchain. Anyway. So we give it the hidden state and the input at every time step, and we just keep repeating that. And that is a recurrent network. But there is a problem here. The problem is that there are 99 of these problems, and no, I'm just kidding. The problem is that so here's the problem. The problem is actually really interesting. So it's called the vanishing gradient problem. Okay, so it's called the vanishing gradient problem. So let's say you're like, what is this? So let's say we are trying to predict the next word in a sequence of text, which is actually what we are trying to do right now, duh. But let's say that's what we're trying to do, and let's say we're trying to predict the last word in this sentence, the grass is green, right? So all we're given, so we know that the word is, green, but let's say we're trying to predict it. So all we're given is the grass is, and we're trying to predict that last word. Recurrent networks can do this, right? They can easily do this because the distance between what the word we're trying to predict, the distance between that data point in the sequence and the previous data points is pretty small, right? The distance between grass, which is the context we need, and green is pretty small. The only difference is that the word is between those two words. And so that's easy to predict because that's the only context that we need. Let's say it had some sentences before that said, the lawn is green, or the grass is, let's say it already said the grass is green, or it's already like the previous sentence, so it already made that distinct connection between grass and green, and those two things are related. So of course it's very easy to do that. But let's also say, that we want to predict the next word in this sentence. So let's say we have a huge paragraph. Not even a paragraph. Let's say we have a 30-page essay. And the beginning of the essay, it is a first-person essay, and it is about a guy named Jean. Okay, he's a French dude. He's got a mustache. Unnecessary details. But a guy named Jean. And it starts off with, I am French, as it should be. I am French. And then there's 2,000 plus other words. And we're trying to predict the last sentence, the last word after 2,000 words, and that is the word French. I speak fluent what? And now let's say between I am French and I speak fluent French, there's all these other languages and so this guy is Spanish, and I heard some German on the subway, and all of that is actually irrelevant to what he speaks fluently, which is French. We've got to know that context. We've got to know that he is French. So of course he's going to speak fluent French. So we've got to find a way for our network to be able to remember long-term dependencies. And so the whole idea behind recurrent networks, the whole reason that we feed in the hidden state from the previous time step for every new iteration is so that we can have a form of neural memory, right? That's why we don't just feed in the previous input, but we feed it in the previous hidden state, because the hidden state is that matrix that represents the learnings of the network, so that we can give it a form of memory, like what it's remembered before and the new data points. But the problem, and you would think, okay, so that's all you need, right? Of course the hidden state is going to be updated more and more, and the whole idea of recurrence is made so that we have a form of neural memory for sequences specifically. But the problem is that whenever we are back propagating, the gradient tends to vanish. So it's called the vanishing gradient problem. So let me explain this. So whenever we're forward propagating, we have our input data, right? And we are trying to predict the next word or character or musical note in the sequence. And so what we do is we say input times wait, add a bias, activate, repeat over and over, and then recurring over and over and over again. And you get the output, which is the prediction. The prediction is the next word or whatever. And so once you have that prediction value, then you're going to say, okay, vectorize the prediction into a number and say prediction minus the expected expected output, which is the actual label or next word or character, because we know it, and because this is supervised. And so then we have the error value or loss value, and then we use that error value to compute the partial derivative with respect to our weights going backwards in our network recursively. We're performing gradient descent, or in the context of neural networks, back propagation, because we are back propagating an error gradient across every layer. But what happens is that as the gradient, remember, this is a chain of operations, the chain rule. What happens is, as we are propagating this gradient value backwards across every layer, we're computing the partial derivative with respect to the error, the partial derivative of the error with respect to our weights, as we are doing that for every layer recursively, the gradient value gets smaller and smaller and smaller. For linear algebraic reasons, the gradient just gets smaller and smaller and smaller. And so what this means is that the magnitude of so the whole point of backpropagation, of gradient descent, is to improve our weight values such that our expected output is closer to such that our predicted output is closer to our expected output, right? We are trying to minimize the error value. And so the whole point of gradient descent is to give our weight values a direction in which to update such that the error is going to be minimized through a forward pass. And so by direction, I'm talking about what values in this weight matrix, this set of numbers, is optimal, such that if we were to multiply this by the input and then do that over and over again, it's going to give us the right output value. And so that's the whole reason we're computing partial derivatives, or gradients, which we also call them, because calculus is a study of change, right? Change, whether it be in moving bodies or change in terms of how to update a set of values. And when I say direction, it doesn't mean like a literal direction like up, down, left, right. It means a direction in that the numbers are closer to the ideal optimal numbers that they should be in the weight matrix. So when we multiply the input by them, the output is going to be closer to the actual output that we want. I probably repeated that several times, but it's good. It's good. It's good for us. And so that's the whole point of performing gradient descent, aka backpropagation. And so the gradient gets smaller. And so what this means is that the magnitude of change in the first layers of the network is going to be smaller than the magnitude of change in the tail end of the network, the last layers, right? So the last layers are going to be more affected by the change, but the first layers are going to be not as affected because the gradient update is smaller, because the gradient itself is smaller. And so, right, and there are two factors that affect the magnitude of these gradients: the weights and the activation functions. And if either of these factors is smaller than 1, the gradients may vanish in time. If larger than 1, then exploding might happen. So that's called the exploding gradient problem. The gradient itself is too big. So it can go either direction. Usually it's a vanishing gradient. But yeah, this is a problem, right? We want to somehow maintain that gradient value as we are back propagating. We want to maintain that error gradient value so that it is at the full magnitude that it should be to update our weight values for every layer recursively in the correct way. We want to maintain that gradient value. We want to remember that gradient value as we back propagate. And so how do we remember a gradient value? How do we remember? Remember is a word, maintain, remember, whatever you want to call it. And so the solution for this is called using an LSTM cell, or a long short-term memory cell. And if you think about it, the knowledge of our recurrent network is pretty chaotic. Like let's say we're trying to, caption a video, a set of frames, a video, right? And it sees a guy and he's eating a burger and the Statue of Liberty is behind him. So then the network thinks, okay, he must be in the United States. But then he's eating sushi and it thinks, oh, he must be in Japan just because it's seeing sushi. But it forgot that he was just behind the Statue of Liberty. There exists sushi places in New York City too, right? And then, he's riding a boat and it thinks, oh, he must be in, the Odyssey or something. But he's still in New York. So we need the information to update less chaotically, to account for all of the learnings, the memories that it's learned over a vast period of time, a vast sequence, to be more accurate. And so the solution for this is called the LSTM cell, and it replaces the RNN cell. And so the RNN cell is input times weight at a bias activate, right? And with that weight matrix that is connecting to itself. And so the difference is an LSTM cell, basically you just replace it with an LSTM cell. You just take that out and you replace it with an LSTM cell. And what it is, it's just a more complicated or more extensive series of matrix operations. So let me talk about what this is. Okay, let me give this a go. So LSTM cells consist of 3 gates. You've got an input gate right here, you have your output gate right here, you have your forget gate right here, and then you have a cell state. Now you also see this input modulation gate, so that's actually only used sometimes, but let's just forget about that. That's Just forget that exists. You have an input gate, an output gate, and a forget gate. And so there are many variants of LSTMs, and that's why you see this input modulation gate. But the most used ones are just input, output, forget, and cell state. So just forget about the input modulation gate for now. Okay, so we've got 3 gate values, and then we have a cell state. So you might be thinking, okay, so what are these gates? Like what is a gate? And so a gate is just like a layer. A gate is a series of matrix operations, and it is input times wait, add a bias, activate. So in a way, you could think of an LSTM cell as kind of like a mini neural network. These gates all have weights themselves. So they all have their own set of weight matrices. That means that an LSTM cell is fully differentiable. That means that we can compute the derivative of each of these components or gates, which means that we can update them over time. We can have them learn over time. And so these are the equations for each of these, right? So for our forget gate, our input gate, and our output gate, it's input times wait, add a bias, activate, where the input consists of the input and the hidden state from the previous time step. So in each of these weights, these gates have their own set of weight values. And so what we want is we want a way for our model to know what to forget and what to remember, and what to pay attention to in what it's learned, right? What is the relevant, and that's called the attention mechanism. What is the relevant data in everything that it's learned? What is the relevant part of what it's being fed in this time step to remember, and what should it forget? The cell state is the long-term memory. It represents what all of the learnings across all of time. The hidden state is akin to working memory, so it's kind of like a current memory. The forget gate, also called the remember vector, learns what to forget and what to remember, right? 1 or 0, binary outcome. The input gate determines how much of the input to let into the cell state, also called a save vector, what to save and what not to. And the output gate is akin to an attention mechanism. What part of that data should it focus on? And so you might be thinking, well, how is, you might be thinking like, okay, so I see these equations, I see how like input times wait, add a bias, activate is akin to forgetting an input and output. I see how there's an ordering to this, right? We have an ordering to this. We first, go through an input. We learn what to forget, and then we compute that cell state, and then we send it to the output. And then ultimately we compute the cell and the hidden state, and these are the 2 key values that we output. So you might see these and you might think, okay, like I see the ordering, I see how they represent forgetting and remembering, but I don't make the connection between still how it knows what to forget and what to remember. And that's the amazing thing about neural networks. These gates are essentially perceptrons. They're like mini networks, right? With a single node, the node is the gate itself, right? It's a single node with a single activation function. All of these gates are perceptrons. They're like mini neural networks, like single layer neural networks. And it learns what to forget, what to remember, based on gradient descent. Again, it's the magic of gradient descent. It learns what is necessary over time. And so these components represent mechanisms for forgetting, remembering, and what to pay attention to, or attention. And so that's what the LSTM provides us. So this equation would be for a normal recurrent network. So you would have your input times your weight plus the hidden state times its own hidden state to hidden state matrix. You'd activate that, and that would give you the hidden state at the current time step. The difference is that it would look like this instead. It's a more extensive series of operations, right? So that's what it is, and so that's kind of the high level of how that works. And now we're going to look at it in code as well, which is going to help your retention. But what are some use cases of this? Like I said, it's all sorts of sequential data, any kind of text, any kind of sequence data. It's gonna be able to learn what the next values in that sequence are, which means it'll be able to both generate and discriminate that type of data that you've trained it on. Right? In this case, it's characters that it can draw. So This is very popular in NLP. Andrej Karpathy, the famous AI researcher, he has a great blog post on this, The Unreasonable Effectiveness of Recurrent Networks. I assume you've read that. If not, check it out. I'll also link to it I'll link to it in the description. And so it's used for translation and sentiment analysis and all sorts of NLP tasks. It's also used for image classification. Like if you think of a picture as a sequence where each pixel is a sequence, predict the next sequence. So there's a lot of different ways that we can frame our problem, and LSTMs can be applied to almost any problem. Very useful. And so what are some other great examples? Well, I've got two. One is for automatic speech recognition with TensorFlow. So yes, it's a little abstracted with TensorFlow, but it's a really cool use case and definitely something to check out. So check out that demo. And then also this repository, which is just a visualization of LSTMs, which is going to definitely help with your understanding to check out this visualization. Very cool demo. It's in JavaScript, I think. Yeah, it's in JavaScript. Oh, no, it's in Python. Great. So yeah, so there's that. Definitely check that out. And so our steps are going to be to look at the recurrent network class. So we'll have a recurrent network class, plain old recurrent network, and we're going to use an LSTM cell instead. So we're going to replace it. And then we'll build that LSTM class, and then our data loading functions for our text, and then we'll train our model. Okay, so what is this right here? This just jumble of numbers with no explanation. This represents the forward pass, the series of matrix operations that we're computing to get our output, our predicted output. Okay, so, and we'll look at this in code. So, okay, so our recurrent neural network is going to, remember, so what we're going to do is, given our M&M text, we're going to predict the input, the next word in the sequence given the previous words. So what that means is the input is going to be all of those words that we have, just every word, and our output will be the same thing, but just moved over one. That means that, it'll look like this. Like, during training, we have a series of, training iterations, right? So we'll say, let's say, my name is Slim Shady would be like the text. So we would say my, and we would try to predict name. Okay, we've got that. Compute the error, backpropagate, next iteration. Weights are updated. My name, and now we're going to try to predict is, right? And so then we say, try to predict is. We have an actual output, we have a predicted output, compute the error, backpropagate, repeat. My name is, I'm trying to predict Slim. You see what I'm saying? So we just keep doing that. And so that's why it's moved over by one. So our inputs and our outputs are going to be our words. We have the number of recurrences that we want to do, which is the number of words total, right? Because we're going to perform recurrence in our network for as many times as necessary until we iterate through all those words up until we get to that predicted word that we need to be at. And then we have an array of expected outputs. And then we have our learning rate, which is our tuning knob for, too low and it's never going to converge, too high and it'll converge, it'll overshoot. And so we'll never converge as well. So that's where our learning rate is. So now let's look at this. So we're going to do a bunch of initialization. So remember, the difference between LSTMs and plain old recurrent nets are that we have more parameters, those gate values, and we have new operations for those parameter values. So we're going to initialize all of those right at the beginning. And look, you might look at this and think, well, this is very complicated and difficult. But remember, with TensorFlow, with Keras, you can do this in 10 lines of code, 20, 30, 40 lines of code. We're looking at the details here. That's why it looks so long. Okay, so that's why it looks so long. So now let's look at this. So we're going to initialize our first word, the size of it, our next word, the size of that, and then our weight matrix. This is the weight matrix between the input and the hidden state, which we're going to initialize randomly of the size of our predicted output. We'll initialize this variable g that's going to be used for RMS prop, which is a technique for gradient descent that decays the learning rate. I'll talk about why we're using G later on. We're not ready for that right now. But then we're going to initialize the length of the recurrent network, right? That's the number of words that we have, the number of recurrences, our learning rate, these are all parameters. And now we're going to have arrays for storing our inputs at every time step, an array for storing our cell states, an array for storing our output values, our hidden states, and then our gate values, right? Our 4 gate values. Well, one of them is actually a cell state. These are our LSTM values. So before that, these were the recurrent network values, and now these are the LSTM cell values. And then we have our array of expected output values, and finally, we have our LSTM cell, which we initialized right here, giving it our inputs, our outputs, the amount of recurrence, and the learning rate, just like we did for the recurrent network. Remember, it's like a mini network. It's like a network in a network. And if you think of the gates as networks, then it's a network in a network inside of a network. Or no, it's 3 networks inside of a network inside of a network. Okay, so yeah, talk about inception, recurrence, inception. So back to this. Those are our initializations, and now we have our sigmoid, which is our activation function. It's a simple nonlinearity, right? And then we have our derivative of the sigmoid function, which is used to compute gradients. That's why we have the derivative, right? We'll talk about that in backpropagation. And then we have forward propagation, which is our series of matrix operations, which I'm going to code. Okay, so for forward propagation, we're going to do this in a loop, right? Because it's a recurrent network. For the number of loops that we want, right? So we're going to say, okay, so for the number of loops that we want, that we define in RL, we're going to set the input for the LSTM cell, which is a combination of inputs. So we'll say, which we can do with the hstack function of numpy, and we'll say I-1 or I-1, and then self.x. LSTM.x equals np self.da. And so this is how we set inputs for the LSTM cell by, it's a combination of inputs from the previous output and the previous hidden state right here, right? So that's us initializing our LSTM cell. And now we can run forward propagation through the LSTM cell itself. So it's going to return our cell states, our hidden states, our forget gate, so we can store it in our array of values, C, which is the cell state, and then the output. And so we can compute that using the forward prop function of the LSTM cell. And so then we're going to say, let's store the computed cell state, right? So then we've got all these values, and now we can store them locally in this recurrent network's memory. These are all values that were computed from the forward propagation of the LSTM cell. And so we can just set the hidden state. We've got our what else do we have? We have our forget gate, of course. The forget gate is going to be set as well. These are all values that we computed in our forward propagation states. We have our input gates, which we're going to set like that. We have our cell state. And then we have our output gate. Right, these are all values we computed there. Now we can calculate the output by multiplying the hidden state with the weight matrix. So, input times weight, add a bias activate. So we'll say, okay, we'll compute that output by saying self.sigmoid. So we'll use the sigmoid function to activate the weight times the input times weight, add a bias activate, right? Yep. And then we'll set our input, because we've computed an output, we want to set our input to the next word in the sequence, right? Because we're gonna keep going. And then when we're done with that, we can return the output prediction. Right, so that's forward propagation. Now for backward propagation, we're going to look at this. So we're going to update our weight matrices. That's the point of backpropagation, to update our weight matrices with our learnings. So we've computed a predicted next word, and we have our actual next word, and we represent these words as numbers, as vectors, so that we can compute the difference between words. Like, how do you compute the difference between words? Well, you convert them to numbers or vectors. Then we can compute the difference to get the error value. So we'll initialize the error as 0, and then we'll initialize two empty arrays, two empty vectors for the cell state and the hidden state. Remember, the cell state and the hidden state were those two values right here, which ultimately these forget input output gates are used to help compute the value of, right? Notice how forget input and output are used here. The forget gate is multiplied by the working memory state, and then we add the input gate, which is multiplied by the working memory state as well, to remember what to forget, to learn what to forget and what to remember. And that's what's stored in our cell state, the learnings of the forget and the input gates. And we then activate the cell state and multiply it by the output to get our hidden state. And so we have our outer level, the weight matrix between the input and the hidden state. We have our hidden state itself, and then the cell state. And those are the key, like, outer level parameters. And then our inner level parameters are those LSTM level gradients, right? So we want the gradient values for our forget gate, our input gate, our cell unit or state, and then our output gate, the internal ones. And so we're going to fill these out. So we're going to loop backwards or backpropagate through time through our recurrence. So we're going to say we have our calculated output. Let's compute the error between that and the expected output. And then we're going to say, okay, we're going to compute the partial derivative by computing the error times the derivative of the output times the hidden state. And so once we have that, then we can say, okay, it's time to propagate the error back to the exit of the LSTM cell, or the way out to the output of the recurrent network in general. So the way we do that, it's 3 steps. We compute the error times the recurrent network weight matrix, and then we set the input values of the LSTM cell for recurrence. We set the input values of the LSTM cell for recurrence, and then finally we set the cell state of the LSTM cell for recurrence. That's pre-updates. And then we recursively call this backpropagation using these newly computed values, right? So this is going to compute gradient updates for our forget, input, cell unit, and output gates, and the higher level cell state and the hidden state, those 2 higher level parameters. And so these are all of our gradients. And now we can, this is just for error logging. Now we can accumulate those gradient updates by adding them to our existing empty values that we initialize right at the start. And then we can update our LSTM matrices with the average of the accumulated gradient updates, and then update our weight matrix with the average of the accumulated gradient updates, and return the total error of this iteration. And that's backpropagation in general. So notice this update step. What this update step is RMS prop. It's a way of decaying our learning rate over time, and this improves convergence. There's a lot of different methodologies for improving on gradient descent. There's ATOM, there's RMS prop, there's ATOGRAD. There's a bunch of these, and RMS prop is one of them. But here's the formula. I'll just put it up there. Okay, so that's what this is. So now so this sample function is the same thing as a forward propagation function. It's what we're going to use once we've trained our model to predict or to generate new words. So it's the same thing, right? We have our input, and for a number of words that we define, we'll say, generate words or predict words for as many iterations as we define. So it's the same thing. So we can just skip that. Now for our LSTM cell. So for our LSTM cell, we've given it the same parameters as we did for our recurrent network. It is, after all, a mini network in and of itself. So we gave it the inputs, the outputs, the amount of recurrence, and the learning rate. And so what we'll do is very similar at the start to what we did for our recurrent network. We'll initialize our input, the size of it, our output, the size of it, and then our cell state is going to be empty. How often should we perform recurrence? We'll initialize that variable, our learning rate as well. And now we're going to create weight matrices. We'll initialize these weight matrices randomly, just like we would for any kind of neural network. We'll initialize weight matrices for our 3 gate values, for our forget, our input gate, and our output gate, as well as our cell state. So the cell state itself, let me go up here, has a set of weight matrices, right? Just like all all neural networks. And so the node has its own set of weight matrices that we multiply to get that output value, right? It's a part of a series of operations, and the weight matrix is that learning part. It's the non-static, it's the dynamic part of that equation that would essentially, you could think of these as gates, you could think of them as layers even, but they're called gates. But layers are very similar, you know what I'm saying? The layers are very similar, input times weight, add a bias, activate. But we call them gates to differentiate, not to be confused with, so many terms here, not to be confused with the actual mathematical term differentiate, but to discriminate, right? Okay, so back to this. So now, where were we? We initialize our gates, we've initialized our gates and now empty values for our gradients that we're going to compute for all of these. Remember, all of these gates are differentiable. So that's where these gradient values will go, so then we can update them through backpropagation, because we backpropagate through the cell itself. We don't just backpropagate through the recurrent network at a high level. We are backpropagating, that is, we are computing gradient values for each of these gates. So we are updating weights for the input, forget, cell state, the output gate, and the outer level weight matrix as well for the recurrent network. So we're computing gradients for everything. So we're updating everything. It's learning what to forget, what to remember, what to pay attention to, the attention mechanism, the output, and the outer level weight matrix as well. So, right. So then we have our activation function, sigmoid, just like before, and our derivative, just like before. And so what we do is we add another activation function here. This is good practice in LSTM networks. You usually see the tan-h function applied pretty much all the time. And you might be asking, well, why do we use tan-h over other activation functions? I've got a great video on this. It's called Which Activation Function Should I Use? Search which activation function should I use? Great video on this. And you'll know it very fast, within 7 minutes if you watch that video. But at a high level, it prevents the vanishing gradient problem. The tan-h function gives us stronger gradients since the data is centered around 0 as opposed to the sigmoid, which is not. And so we use that. And then we also are going to import the derivative function of it because we want to compute gradients. Right? Everything is differentiable. So just like before, we'll compute the forward propagation for an LSTM cell. And so remember, the forward propagation for an LSTM cell is, drum roll please, this set of operations. Ultimately, we want to compute the output, right? We want to compute the output. So that's what we'll do. Back to this. So we'll say the forget gate is going to equal the input times the forget. So we're going to activate the dot product of the forget gate and the input. Input times forget gate, and then activate. That's going to give us our forget gate, and then we're going to compute the cell state. We're going to update the cell state by multiplying it by that forget gate so it knows what to forget. And then we're going to compute the input, which is going to be, again, the activated version of the input times the previous input. The current input times the previous input. And so that's going to tell us that. And so then, once we've got that, we can compute the cell state, which we're going to apply this new activation function for the cell state to prevent the vanishing gradient, which is the cell state times the input, and then we activate, right? That series of operations. And then we're going to update the cell state by adding the input times the cell state. The cell, input times the cell. And then for our predicted output, we're gonna take those, we're gonna say, let's compute the dot product between the output gate and the cell state. Or no, the output gate and the input. And that's gonna go to our predicted output. And so what we can do is we can say, oh no, that's going to give us our output gate. And to get our actual output, our predicted output, we'll multiply our output gate times the activated version of our cell state. And that's going to give us our predicted output. We can then return our cell state, our predicted output, for get gate, input gate, cell, and then our output gate as well. That's forward propagation. All right, and that's the equation that I showed up there. So now we've got our forward propagation. Now we're going to look at the backward propagation. Remember, we back propagate through the cell state as well, not just the higher level recurrent network. So what this is we're going to compute the first error, right? So that's the error plus the hidden state's derivative, and we'll clip those values so it's not too big. We want to prevent the gradient from vanishing, so clipping it helps that. And we'll multiply the error by the activated cell state to compute the output derivative. And then we'll compute the output update, which is the output derivatives times the activated output times the input. And then we'll compute the derivative of the cell state, which is error times output times the derivative of the cell state plus the derivative cell. So we're computing derivatives of all of these components in the backwards order as before, which means the forget gate computation or update will happen near the end instead of near the beginning. And so then we're computing the derivative of the cell, and then the cell update, the derivative of the input update, the derivative of the forget update. So you see what I'm saying? We're computing gradients and then we're updating them, right? And then derivative of the cell state, and then the derivative of the hidden state, and then finally we can return all of those gradient values, those updated gradient values for the forget, the input, the cell, the output, the cell state, and the hidden state. So many different parameters that we have computed gradients for, and backpropagation is going to let us compute all of those, right? Recursively, computing the error with respect to our weights for every single component we have in that network in the reverse order that we did forward propagation. And so, yeah, it's just, you know, it's more matrix math than we did before. It's like 6 or 7 more steps than a recurrent network. Maybe it's more like 8 or 9 more steps, but yeah. And then our update step is going to just be us updating our forget, input, cell, and output gradients. And then we can update our gates using those gradient values, and they're our gradient values. Okay, so then that's it for our LSTM cell, our recurrent network, and now we can look at our load text and our export text function, which are not as interesting. But what we do is we load up our M&M text file of lyrics, right? Just like that. And then we compute those unique words for all of them, and so we have a sequence, right? We have a sequence, our input and output sequence. And then we have this export text, so whenever we've sampled new words, we can write them from memory to disk, that's all. And so for our program, we'll say, okay, so for 5,000 iterations with a learning rate of 0.001, let's load the input and our output data, and then we'll initialize a recurrent network using our hyperparams that we've initialized before. And then for training time, for that given number of iterations, 5,000, we'll say compute the predicted next word, so that's the forward propagation. Then perform back propagation to update all our weight values using our error. And then if our error, and then just keep doing that. And then this catch, or this if statement will say, if our error is small enough, that is, it's between this range here, then we can go ahead and sample, which means predict new words, generate new words. Our network is trained, our error is smallest. Let's go ahead and now just predict new words without having to compute backpropagation to update our weights. Our weights are already updated enough. So then we can go ahead and define a seed word and then predict some new text by calling that sample function, which is the forward propagation, that's all. And then we can write it all to disk. All right, so let's run this. It's beginning, it's gonna take a while. And then once it's done, I actually have a saved copy. it's spitting out some pretty dope lyrics, right? These are some pretty dope lyrics, right? That's it for this lesson. Definitely look at this Jupyter Notebook afterwards. Look at those links that I've sent you in the description as well as inside of the Jupyter Notebook. And make sure that you understand why, at least why to use LSTM cells. The reason is because it's to remember long-term dependencies. That's at least a high level that you should have got from this video. It learns what to forget, what to remember, and what to pay attention to. Those are the three things that an LSTM cell, as opposed to a regular recurrent network, lets you do. Okay, so yeah, please subscribe for more programming videos. And for now, I've got to learn to forget. So thanks for watching.